Polynia is a word you heard many times this week. It's like the fricadelles. So everyone talks about them, but no one really knows what they are. And I think Dirk is going to give you some start kit on Polynias. Dirk, the floor is yours.
Yeah, I'll try at least. Okay, so it'll again be a bit of a whirlwind tour, but we try to sort of follow this rule that often you can learn 80% of something within 20% of the time, and then the other 80% of the time you spend on understanding the details, and we don't cover the details, so that makes it kind of efficient. So we start off with the technical definition. Polynias are non-linear shaped openings enclosed in sea ice. So here's a picture. So we have some landfast ice, the Polynia, and then the pack ice. So Polynia is open water where you wouldn't expect open water. That's my definition. And there are two major types of Polynias. One are traditionally called latent heat Polynias. I actually prefer to maybe call them coastal Polynias or shelf water Polynias because they usually form close to the coast. And the way they work is that you have a non-moving boundary, which can be an iceberg, it can be landfast ice, it can be the shore. You have wind blowing over it, and so the ice starts moving. And because this stuff doesn't move, there is a gap in between, and this gap is filled with the ocean. And the reason why they are called latent heat Polynia, in particular in winter, this water will be at freezing temperature. And so you expose the open ocean to the atmosphere, and there's a lot of heat exchange, a lot of heat coming out of the water, and because the water is at freezing temperature, the heat that you remove from the water is not sensible heat, you don't make the water colder, but the heat that you remove is latent heat, you form ice. Okay, and so these latent heat Polynias, they require some non-moving boundary, and they are wind-driven, and so they often form around the same locations, but they can vary temporally very quickly. If the winds change directions, they close up within whatever day or two, and then they can open up again next day or something. So they are temporally quite variable, and they are incredibly efficient ice growth factories. So maybe if we just quickly recall our expression for the heat flux through ice. T top minus T bottom over the ice thickness. If we assume an ice thickness of, say, 2 meters and our heat conductivity is 2 watts per meter in Kelvin, those twos cancel. And so the number that you get for the heat flux is roughly the temperature difference between top and bottom. So if that temperature difference is 10 Kelvin, you get a heat flux of 10 watts per square meter. So the order of magnitude of heat fluxes that you get through the ice, through existing ice, is 10 watts per square meter. Whereas the order of magnitude of heat fluxes you can get between open water and the atmosphere is hundreds of watts per square meter. And so therefore, basically ice formation in a Polynia is at least 10 times more efficient as if you wouldn't have that Polynia. And therefore, even a really small area of open water somewhere can very quickly dominate ice production in a specific area. And then with all this ice formation that you have in here, you release salty brine. So these latent heat Polynias are also very good at transforming water masses, at making the ocean more salty. Coastal Polynias or latent heat Polynias?
I think the number is less than 1% of surface and more than 10% of production.
Something like that, yeah. Any questions on that? Good, yeah. To form what? Yeah, and because it's wind-driven, it can happen within a day, basically. As soon as the wind changes and picks up, it starts moving the ice. It's a bit of inertia, but I would say order of magnitude days. And then the other big type of Polynias, if that's kind of okay, are sensible heat Polynias or open ocean Polynias. And these are Polynias that form somewhere out in the blue. Most famous example on the globe is the Weddell Sea Polynia. And they basically occur because there's warm water coming up from below. And so they are driven by oceanic processes, sometimes very, very complicated oceanic processes. So if you look into the literature as to how the weddelled sea polynya comes about, there's all sorts of stuff of Taylor columns and other sort of oceanographic stuff that I won't talk about, so it's an oceanographic problem where this thing comes from. And they're called sensible heat polynya because the warm water that comes up here is then in contact with the atmosphere. You remove a lot of heat, but because the water is warm, the heat that you actually remove is sensible heat. You make your water colder, you make it denser, so the water sinks again and is being replaced by more warm water from underneath. And so there's no ice formation in these sensible heat polynyas. And because they are oceanic driven, their timescales is much, much longer. So the weddelled sea polynya, for example, was there in the 1970s for like 5-6 years, simply because the oceanic conditions remained relatively stable over these 4, 5, 6 years. And again, they would usually form in very similar locations if they formed once, because you need, for example, a seamount, you need certain specifics of tidal currents or something, some mechanisms to bring warm water up to the surface. Yeah.
Are these going to be transient, kind of one-off events, or are there any regions where there's a constant supply of water?
There are regions where there's a constant supplies of warm water, for example, in the Weddell Sea. Even if you don't get a proper polynya, the ice is usually thinner there than around that region. So there is a constant oceanic heat flux in those regions. But there's famous polynyas also in the Arctic, like Whalers Bay polynya, that basically are always there. And that is because you always have warm water coming up to the surface in these regions. Yeah. Because the water that comes up from below and that melts the existing ice is warm. And as you start cooling it, you make it denser, and so it sinks again before it reaches the freezing temperature. So you're basically unable to cool the water down to a freezing temperature, and so therefore it's not possible to form ice here. Why is it upwelling? That's an oceanographic problem in the Weddell Sea polynya. For example, there's a seamount, and it doesn't need to be upwelling. It can just be columns of warm water that pass through the area. There could be tidal currents that are steered by topography, for example. So there are all sorts of reasons, often related to the specific of the seafloor and of the oceanographic currents in the area. Yeah, well, the Weddell polynya was huge, was bigger than France, I think, if I recall correctly, because the region of the upwelling was very large. Coastal polynyas can really be anything from a couple of 100 meters to some kilometers away from the shore.
Yeah, I mean, the thing that's interesting is it's actually very hard to get that much upwelling over a large region. It's like the convection we were talking about, and you've drawn there what's going up.
Mm-hmm. Something went down again, yeah.
Kind of interesting, actually, oceanographic.
Yeah. Therefore, there is hundreds of papers trying to describe what's happening there, and I've really shied away from. I tried to go. Well, I did go into some of this literature, but I quickly realized this is way beyond my understanding of fluid dynamics and convection to figure that one out. It's a really tough problem. You could. The problem is we have very few of these, and much of the upwelling, we do have upwelling in the Southern Ocean that doesn't form polynyas because it never reaches up to the surface, for example. We usually use it as indicating something really bizarre is happening in these few spots where we have important sensible heat polynyas. I'm not sure if it's a kind of, for example, if we run a climate model, we often have the problem that we always get a weddelled sea polynya, for example. And so somehow the model is recreating something that makes warm water come up to the surface. if that is what you mean by predicting. So the physics of what is happening here is existing in ocean models, and so they would often form thin ice in similar regions as we also find them in reality.
I would say it's the first problem you encounter when you try to run an ice ocean model in the Southern Ocean is that you have Polynias everywhere.
Yeah.
And people try to stabilize the growth of sea ice and the vertical convection. So that's...
Oops, sorry. Great, and, sorry. Yeah. Yeah, so there's the sort of famous one would be the Whalers Bay Polynia in the Arctic off the Greenland coast, where you and it's called Whalers Bay because the whalers knew there's always open water, so they would go there in winter and hunt whales. Yeah.
So there's no sea ice production
No.
locally because of the upwelling, but the presence of these infer more easier sea ice production locally because you're cooling up the
No, because the water you have up here is warm, and so you extract heat, but that heat is just being used to make your water dense and then disappears into depth again. And therefore, once you have a Polynia, for example, in the Weddell, it can last for years. Yeah.
So going back to the lake between,
Yeah.
again, the same question about predicting it. There it would be just a matter of getting the atmospheric forces right. But we don't have very good reanalysis or anything that can even predict katabatic winds correctly.
Mhm.
How can you really rely on your model there?
Depends on what you mean to rely on. And so, first thing, if you have a Polynia along fast ice, then you also need to get your fast ice to not move, and that is incredibly tough for models. Usually, they want ice to move around. But in principle, because katabatic winds are sort of a standard feature of Antarctic, most models would have offshore winds, and so most models would create Polynias along the coastline. Not always in the right location, not always to the right magnitude. It's in order to do that, you also need to know how thick is your ice, what is the inertia, and stuff like that. But the first order, this is relatively straightforward to model. But then, if you look into the details, it gets hard.
Okay, and then what sort of atmospheric gases would be then used for forcing?
I would use some, well, depends on what you want to do. The problem is really that, as you say, the katabatic winds are not well represented in any of these reanalyses as far as I know. So you might have to do some bias correction. I would just use some era forcing, for example, and then just see how well the Polynias match what we actually observe.
There is another problem is that there are also suspected atmospheric feedbacks, and I think that this is the topic of the thesis of Matthias that is there, that you may actually have retroaction feedbacks on the atmosphere of the presence of Polynias on the atmosphere that might not be resolved in your reanalysis. So, not easy.
Yep. Sensible heat, because it is melting the ice basically. Yeah, I'm not familiar how often. Is that something you would know about, that this happens somewhere? It's not something I've heard about very much. So I'm not sure how much warm meltwater we have in winter when sort of there is information. Okay. Okay. Yeah. Okay. Yeah. Okay. Okay, cool. Great, thank you. Yeah. Yes, exactly. Great. So what I would like to do next, just very briefly, because these things, as we've just seen, really are ice factories, I would like to briefly sketch a very simple model that explains us how big these things get, because it has some interesting features. So maybe so my intuition, I'm not sure if you would share that, is that the size of these Polynias primarily are given by the wind speed. Can we all agree on that? if we have really strong winds, they should get large, and if we don't have strong winds, they don't get large. And that intuitive understanding is wrong. The size of these Polynias is not primarily depending on the wind speed. And so maybe let's quickly bring this up again. Maybe I just... And so the idea of the size of wind-driven Polynias goes back to the 1960s by Lebedev, and then 1980s there's a paper by Pease that models wind-driven Polynias. And the general idea is that the size of the Polynia is governed by the amount of export of ice given by the wind speed and the amount of new ice production in the Polynia. And once these two are the same, the Polynia size doesn't change anymore. And the amount of ice that you export is just given by the wind speed, but the amount of ice production in the Polynia actually is proportional also to the size of the Polynia. The bigger your Polynia is, the more ice you obviously produce. And let's just do a very quick schematic of our Polynia. So what this is supposed to show is that if we have wind blowing in this direction, and we neglect Coriolis and all these complicated things for now, everything is 1D. We move pack ice away from the coast, so we form open water. In this open water, we form Fresnel ice crystals, which also then are driven by the wind to this edge here. And so if this is our Polynia size as a function of time, and this is our area covered by Fresnel, and this stuff has a certain velocity, then I think we can all agree that the change in Polynia size over time is given by the speed with which this ice moves away minus the speed with which the Fresnel area is growing. And the area, and this term here, that is simply given by the amount of Fresnel that we form, production of Fresnel, divided by the so-called collection thickness. Of the Fresnel. So you have to imagine we form whatever billions of tons of Fresnel in here, and then we push it together, and it will pile up to a certain thickness here. It won't pile up to just a centimeter, it won't pile up to whatever, 5 meters. So often a good assumption is like for this stuff, maybe 30, 40 centimeters or so. And the total production of Fresnel, that is proportional to the size of our Polynia times the production rate. So the production rate is Fresnel formation per area. And the bigger our Polynia is, the more Fresnel we produce. And this then changes the amount of Fresnel that we have somewhere. And if we put all this together, what we find is that the change in our Polynia size is given like this if HF is our collection thickness. So just to revisit this, the Polynia is getting larger because our ice is moving away, but it's getting smaller all the time because our Fresnel covered area is growing, and it's growing because we produce Fresnel over the entire Polynia area. Does that make sense? Yeah, all good? Cool. And the thing that we're interested in is what is our equilibrium size of the Polynia. So we set the left-hand side to 0. And we can then, this is a bit too messy, so I write it over here. The equilibrium size of our Polynia is then simply given as U times H F divided by P. And maybe I do like this. And so the speed with which our pack ice is moving is a function of wind speed. And the production rate of Fresnel is also a function of wind speed and of air temperature. If it's really windy, we have a lot of turbulent exchanges, so we extract a lot of heat. And if it's really cold, we also extract a lot of heat. So our production is a function of air temperature and wind speed, and our the speed of the ice is a function just of wind speed. Does that make sense as well? Yeah, cool. And since both these terms are, generally speaking, proportional to wind speed doesn't matter for the final size of the Polynia. But the final size of your Polynia is primarily a function of temperature, interestingly. And so this is the model by Pease. I think it's 1987 or so. And what that means, if we get, for example, global warming and our temperature will rise, if we assume that the wind speeds stay the same, it means that our Polynias will get larger, but again, they will reach an equilibrium size once the ice formation in here is the same as the speed with which we export ice. And so when I was thinking about this, I think yesterday it was, I figured that then in theory, the ice production in Antarctic Polynias should be relatively independent of air temperature. Because you just change the size of the Polynia until the amount of ice you produce in here is the same as the ice export. And if the ice export stays the same because the winds stay the same, in a warmer climate you get bigger Polynias, but the total amount of ice formation stays the same. And I'm not sure if that's true, so here's your whatever PhD master topic for some time to come, to just figure out whether that is correct to first order. But it should be if you trust this very simple approach to modeling latent heat Polynias. Yeah. The what? They have bigger Polynias. Yeah, because they need a bigger amount of ice formation. They need a bigger area to sort of make up for the ice that they're exporting. Yeah. Yeah, but the assumption here is that it's all at freezing temperature. Mm-hmm. Yeah, and this is, and then these are not latent heat Polynias. If the water is warm, there is no ice formation, and then all of this doesn't work. So this is not a model to describe Polynias in areas of warm water. So the temperature of the water for this model to work must be very close to freezing. Yep. 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 Because the balance that you have in equilibrium is always given by the fact that the amount of ice that you export is balanced by the amount you produce in the Polynia. And if your ice export, if you assume that that stays the same in a warming climate because maybe the winds stay the same, then your ice production also must be the same to reach equilibrium. But you need a larger area to do so if your temperature is higher. Yep. So it's a nice, simple model, and I've never really started to think about the implications of that in a global warming climate. So I'm sure there's some really beautiful master thesis or PhD topics in here. And that's generally what we wanted to do regarding Polynias, unless there's one or two slides that you would like to show, I think.
Yeah, I just wanted to add one thing regarding Polynias, something that connects to real situations. Yeah, maybe the point I will try to make here is that there is another dimension in the problem, is that we are still trying to understand what sets the location of Polynias and what type of processes that drive them. So in principle, we know you need wind, you need export of ice, and you have production. But in practice, you don't observe Polynias everywhere. And there is one point that has been raised over the last decade, is that Polynias in the Antarctic are really associated with the presence of landfast ice. And when I saw this plot, like 9 years ago, probably, maybe I missed the paper in 2015, but quickly after I saw it, you see that whenever you have fast ice in blue, you have a Polynia. The whenever is maybe a bit too much, but in the majority of cases, you see a strong association. So that's another element to consider. So the fast ice is in blue and the Polynias are in red. And both Polynia and fast ice can be detected by remote sensing, and we have like 20 years time series now, and so that would be a climatology map. That's the Japanese version of it, and I think there is an Australian version of it that is also very close. And so the hypothesis raised in this paper is that there is an association between both, and they hypothesize that the mechanism is that fast ice is locked, and it acts as land, it acts as a barrier that leaves the floor for Polynia development. So I forgot to put the wind here, but if you have wind blowing that way, you have the fast ice that is locked, and then whenever the fast ice is not able to be sustained anymore, you would have a Polynia. So that's another dimension of the problem. I'm not sure we can fully reconcile it with the Pease model. Maybe it's just another dimension of the problem. You see, science is being developed. And one thing I may add to add a bit of element is ongoing work by a PhD student in Louvain-la-Neuve. He's called Noé Pirlet. And he's tried to do a first step to impose a landfast ice in an ice ocean model. And what he found is that when you do that, you actually resolve much better Polynias. So it's a figure that he put together. And so we have more evidence after this that the presence of Polynias is really helped by fast ice. And then the problem is to resolve the fast ice. And to resolve the fast ice, we are in trouble because, as I mentioned, we need icebergs and also anchoring the big icebergs. And for this, we are still not very far. First, we don't resolve necessarily the biggest icebergs from the icebergs model, but we don't also know the mechanisms of anchoring that need to be studied. So it's also a place where there are good PhD and master studies and so on. There are several groups working on that. So it's complicated because you really have a connection between the continental cryosphere, the icebergs, the fast ice, and the Polynias. That in the end will influence your dense water formation. So that's, I think, in terms of complexity, it's hard to do more complex. You have connections between 3 or 4 compartments of the Earth system. I think it's a unique case. I think you see opening of, I don't know, offshore, I don't know, close to big drifting icebergs. You can see that in the lee of those icebergs. There was Takenobu Toyota, I think, has done work on this. I think this is all. I wanted to add the fast ice element to Polynia, and I think this is it. So we have 20 minutes left, Dirk. What do we do?
What do we do? Maybe we do a quick.
Do we do this tipping point feedback thing?
We could do a quick tipping point feedback thing on.
We had an
nodding.
Australian student asking for feedbacks.
And so we do that quickly, maybe just a 5-10 minute, and then we maybe have some details on Southern Ocean sea ice. What do we know about past, present, future? And then we overrun by 5 minutes because we've been so good at keeping time that we now take the liberty to overrun.
I'm keeping
JB was just not there, but now he's back, so I shouldn't have said that probably.
We are not that bad, huh?
No. So what we thought what we do with feedbacks is to maybe use that to briefly talk about tipping points, tipping elements, whatever. And so in the story with sea ice goes, it's very reflective. Sorry, picture from the Arctic. It's very reflective. So if we get less of it, we get more absorption of sunlight. And so there's a really strong feedback loop. So if we have less sea ice, we get less reflection of sunlight. We get warmer water, we get less sea ice. Very, very simple story. And that story has led to the introduction of the term potential tipping points into the scientific literature. And as far as I could find, the first 2 papers in the natural sciences geophysical discipline that used the term tipping point were both related to sea ice. Arctic sea ice actually passed the tipping point, or does Arctic sea ice have a tipping point? And also, in terms of public awareness of the term tipping point, the first large-scale coverage of this term is from 2007, when we saw a rapid decrease in Arctic sea ice. And so there was this public coverage of has Arctic sea ice crossed a tipping point. So the history of the term tipping point is fairly closely related to sea ice. The problem with all of that is that it doesn't really work for Arctic sea ice. And we did a bit of work on that back in the days. And the main argument that we used, so I did a thing on there is no tipping point in 2009 in PNAS. The main argument that I used there was simply looking at observations of Arctic sea ice, and what you find is that whenever sea ice decreased in one year, it always recovered the next year. If the ice albedo feedback would be dominating, you would assume whenever you have very little ice, you should have even less ice in the next year. But if you look at the year-to-year changes, you find a negative autocorrelation from one year to the next, which basically says these amplifying feedbacks apparently don't carry over from one year to the next. So simply by looking at the time series, there's strong evidence that there is no self-amplification in Arctic sea ice. And you might wonder why that is, and we briefly talked about that yesterday already. So if we have a winter situation after summer with very little ice loss, so the ice is thick, we will have little heat loss from the ocean and so little ice growth. Whereas if we have a summer with substantial ice loss, there's lots of open water, there's very thin sea ice, there's very little snow, so we have lots of heat flux from the ocean into the atmosphere, lots of sea ice growth, and so the system recovers to some degree. And so if you want to make this a bit more schematic, if you look at some of the feedbacks that are relevant in Arctic sea ice, if we have less sea ice and we have more open water, we do have one positive feedback, dominating or big positive feedback. That's the ice albedo feedback, but that only works in summer. And in summer it is important, so if you have very little ice, say in June, you probably also will have very little ice in September because the ice albedo feedback works throughout summer. But then as soon as winter comes, if we have a lot of open water, we have more outgoing long-wave radiation, we have later sea ice formations, so lots of the snow actually falls into the water rather than landing on the ice, so throughout winter we have less insulating snow, so we get more sea ice. We have a thinner ice cover, so a higher growth rate, we get more sea ice. And what we see from observations and also from the models, these processes dominate, otherwise we wouldn't have sea ice in the Arctic. going back to papers from the 1920s talking about small ice cap instabilities. And so all these processes are really, really very basic sea ice physics. And so the large-scale response of sea ice to global warming is really governed by fundamental physics that is represented even in the very, very simplest sea ice model. And for me, that is, for example, a reason why the sensitivity of a global model to warming doesn't depend on, when it comes to the sea ice, doesn't depend on the complexity of the sea ice model. So what is shown here in the as the green line is how much sea ice we've lost per degree of global warming in the observational record. There's only sort of one model that loses more ice. All the other models lose less ice per degree of global warming. And the red models, those are the ones that have very, very complex sea ice components. The gray lines are ones that have very simple sea ice components, and it's basically all over, because the dominating processes you would have even in the very simple models. And so for the Arctic, I think I skip winter time. And in winter time, just briefly, in the Arctic sea ice loss, we have an acceleration at some point, but that's simply related to the fact that eventually we detach from the coastlines, and so then there's more opportunity for the ice to retreat. Therefore, winter sea ice loss will eventually accelerate, but there's no magic process involved in that. And so what we did recently to put together a report on global tipping points with Ricarda Winkelmann leading this exercise. And what we concluded, these minuses here, tipping system confidence level, very, very certain that Arctic summer sea ice doesn't have a tipping point. Probably also not Arctic winter sea ice. Probably, maybe not Barents sea ice. And the one thing that I would like to conclude this story with, if you look at this map, there's low, medium, high confidence for all components except for one. Antarctic sea ice triangle, we really don't know. And for me, this is a beautiful map, again, to tell you why we need more people working on Antarctic sea ice. It's really the one cryosphere component where I wouldn't dare to make any guess on whether it is a tipping element of the climate system or whether it isn't. That is my very short story of importance of feedback, positive, negative feedbacks, that if this story sounds too simple, it sometimes is useful to look twice. And I think you may have one slide on a bit more complicated feedback stuff, and then we see what we do next.
We didn't have any material ready to list all the possible feedbacks in the Antarctic sea ice ocean system to satisfy the question of our Australian student.
I'm sorry.
No, it's the wrong. It's metal. But I can recommend a reference. It's of course it's selfish as usual because I'm co-author of the paper, but I didn't do much. There is this paper by Hugos and many others that results from long discussions during a workshop on polar feedbacks led by Hugos and Jen Kay. And in this paper, you have a framework of analysis that is developed. But interestingly, you have one figure that describes all the possible non-linearities in the system, and it includes a lot of elements. And then there is this table that took forever to put together. That was a bit of a crazy exercise to consult all the specialists of all elements of the system and to have a concise table that describes the name of the feedbacks, their description, and how you can measure them. And also you have references here. And for example, you take the most known feedback, which is the surface albedo feedback. Melting ice and snow lowers surface albedo, leading to increased absorption of shortwave radiation and amplified warming. And you can measure that by a change of top of atmosphere flux due to surface albedo change divided by surface temperature changed, and you have a list of references. So that's one feedback that was mentioned by Dirk. The other feedback would be the growth thickness feedback, which is the most active negative feedback that explains the absence of a tipping point, I would say, in the Arctic. So the Arctic would be these just two, but then you have plenty of other things that are on the table, and that I would say we don't really know how they play a role in explaining the change, and they are there. They have been identified. For example, you have these two key ice ocean feedbacks. No, the table does not continue, but I was trying to look at ice production and entrainment feedback is the one I mentioned yesterday, that is active when an ocean is not very stratified, and that really responds in terms of heat to ice growth. But you will see that there is another one I didn't mention, that is linking ice production and heat storage. And I will not go into the details here, because it would probably take too much time, and I'm not fully prepared. But really, for those who are interested in this topic, this is really the reference I would consult. And if you are interested in one of the processes, you can check the references. And next summer school, we will prepare a full description of all the feedbacks. Are there any comments or questions on this part? Yes? You mean the production, ice production, ocean feedback? One of them really relates to the fact that when you produce ice, you bring in immediately heat in the surface layer and then dampen the production of ice. And the other one is more complicated. It's over several years that if you produce more ice, then you tend to store more heat in the subsurface ocean. And I have a hard time to really nail down that one. I know Hugues is really into it, and he says it's important, but I'm not sure I fully grasped the whole thing.
Any other questions on feedbacks, tipping, this kind of stuff? Good, because there's so many things we don't know. So most questions we probably couldn't answer anyway. Then we use maybe the last 10 minutes to look at some of the specifics of what actually happens in the Southern Ocean now and what we know about the future. Unless there's any other ideas what we should do. No, then we just move
we
forward.
have about 10 minutes left, I think, if my smartphone doesn't lie. Okay, so one thing I will do is to advertise the poster of Kenza. And Kenza just finished her PhD thesis about recent changes in Antarctic sea ice. So we've heard a lot on the change in Antarctic sea ice already, I think, this week. Okay, so I'm really stealing Kenza's thesis results. But the thing she did was part of her PhD that she recently defended, and really adopt a sea ice point of view on the problem of recent changes, because people always look into the atmosphere or the ocean, and our role as sea ice people is to look actually of what's happening in the sea ice. If you want to know more, I think you can just go to her poster, which is hanging on the street. I think she doesn't really like the poster. That's what I heard, but I think the work is cool and it's original. Voilà. So I think the question that is treated here is that we have rapid Antarctic change in terms of Antarctic sea ice coverage after 2016. And the question I will address in these five minutes is why do we have such change on a very sea ice-istic point of view? And on the sea ice point of view, the way you can ask this question is whether it's due to drift or to growth and melt. That would be the thing that you would try to look at, not to look at necessarily atmospheric causes or oceanic causes, but more at the sea ice processes. And to do this, she used two angles of analysis, and I will try to explain you a bit what are these two tools. Maybe that's an interesting point for you. One is the sea ice seasonal cycle. You can look at how the seasonal cycle changes, and that will give you hints at what causes them. And the other is what we call the sea ice concentration budget. So you basically calculate a budget equation for sea ice concentration and see how it changes in time. I will give you a bit of background on the first point. So the seasonal perspective is something that we are exploring since a few years. I think Sharon Stammer-John was the first to introduce the retreat and advance dates based on ideas she developed with Dirk Martinson some decades ago. And basically you summarize the seasonal cycle as an ice season and an open water season. And here you have two dates. The retreat date is when there is no more ice, and the advance date is when you start the ice season again. And so Sharon showed that actually these two dates have some specific dynamics that look interesting. And what Kenza showed in this thesis, in her thesis, is that you can actually relate in the climatological mean state. You can relate this retreat and advance dates to other properties of the seasonal cycle, which is the maximum winter thickness, or the thickness that is reached at the end of the winter season. And same for the advance dates. It's really related to the maximum mixed layer heat content that is reached. And you can see these scatter plots. These are based on observations and on climatologies. And you can see actually that the relationships are reasonably significant, especially this one. There was publication specifically on this link that you can actually know very well when the ice is going to start if you know how much heat has been accumulated during the winter. And those are 2D histogram based on spatial distributions. So this framework shows that actually if you look at the seasonality problem, there are links that go throughout the season. This one, for example, is the retreat date that will decide the mixed layer maximum heat content. So this is this link. And we also see that the retreat date seems to be reasonably well correlated with the maximum thickness. And this all physically and thermodynamically makes sense because the thicker the ice, the more time you need to melt it. The later the ice retreats, the less time you have to accumulate heat in the surface ocean. And same for advance, the more heat you have, the longer you need to lose this heat. So the next question was, can we know more about recent changes based on such a perspective? And first thing Kenza did was to look at the time series of all these parameters that I've mentioned in the previous slide with time based on satellite observations. And so you have here all of these parameters. You have the retreat date, and so you see a time series. You see that the retreat has been earlier and earlier over the recent period. The advance has been later, so the sea ice season starts later and later. The thickness in September has been thinner and thinner according to observations, and the SST, summer maximum SST, has also increased. So everything seems tied together. Okay. The summer thing, so the warm SST and later advance, according to her analysis, seems to be really a thermodynamic effect of early retreat. So this is supported first by spatial patterns that match between the different things. Earlier retreat coincides with warmer SST in 85% of the regions, and later advanced coincides with warmer SST in even more larger. So that's suggests that what happens in the summer is essentially a thermodynamic response of earlier retreat. And then the next question is why we do have this earlier retreat of sea ice. And to do that, it was a bit more complicated, and this is where the sea ice concentration budget arrives. So that's an idea that has been introduced by Paul Holland and Ron Kwok some years ago. And basically, you use a satellite retrievals of ice concentration and ice drift to get the budget. So this you can measure. This is the concentration change in a local point. The velocity vector you also have from observation, so you can estimate that term. And so you have, you can calculate this, assuming that the budget is closed, and it's a residual, but if you think a bit about it, you discover that it's actually the thermodynamics. Because, yeah, there is no other reason why we would not close that budget. And so one thing that we really saw by calculated this budget is that the I don't show the maps. I think it's in the poster, but that the dynamics have really no, it's not on the poster. Sorry, you have to ask Kenza if she really wants to open her computer and show you the plot about this. But really, the sea ice concentration budget suggests that changes are thermodynamic because we don't see a lot of things happening in terms of dynamics. So you have several other things in there, but we also see that the thermodynamic term is actually changing over the last period, the recent period. The sea ice concentration loss rate is increasing, which we argue is an effect of the ice albedo feedback. So, yeah, I don't come into the details, but the analysis really illustrates that the later retreat is an effect of thinner ice. And then the next question that we could not really answer because we didn't have any data to look at or any time would be more precise, with why would the sea ice be thinner in the first. And that seems to be the origin of the thing. And so that would be the summary of what she showed. So the recent change in this Antarctic sea ice seasonality points to change in retreat date and advance date. And it seems to be really a thermodynamic response to winter ice thinning. And addressing the reason why ice is thin is beyond what was done and yeah, need to be further explored. One last point is that things seem to be a bit spatially uniform over the Antarctic zone, and so that would be more consistent with change in the ocean. That would explain why ice would be thinner. And I think that was about what I wanted to say in here. I thought that was an interesting perspective to add to what has been said on the atmospheric change and on the oceanic change. We also see things in the sea ice and we start to understand them. Yes? Yeah. Sorry? Yeah, no, I didn't get the question, sorry. Yeah, it's hard to say. We struggled a lot.
negative winter effects that we presented. So that's why
I think we are close to the end of our time. Are there questions, CI's questions left? Oh,
Yeah, I think there was one question just before about the future of Antarctic sea ice. Very simple answer, we don't know. When we looked at CMIP6 model simulations, they are so all over the place. I mean, they all have less and less ice over time. So I think that's probably what we can say with some robustness. But how quick things are happening, how different things are in the different scenarios is unclear. Yes. So this is So this is just some illustrations. So the black lines are the seasonal cycle of Antarctic sea ice in the observations, and the green lines are CMIP6 models seasonal cycles. So if you look at the winter maximum, some have whatever 2 million square kilometers, some have 20. And in summer, some have whatever 7.5 million square kilometers left, some have no ice left. And this spread just for us made it almost impossible to say we trust which of these models should we trust. So I would say we really don't know, which also then is this whole tipping thing. We also don't know. Anything that relates to the future of Antarctic sea ice, we don't know, simply because we're only just starting, as Martin was just showing, to understand the present. I would ask an oceanographer to help me.
I think I had this plot. One thing that you clearly see from projections is that also the mixed layer depth is completely all over the place in this Antarctic sea ice zone. And my first take to improve our system models in the Southern Ocean is really to better constrain the links between surface ocean, heat, budget, and the sea ice. I think that's the most obvious thing I would see. And I think I even have had that in my recommendations of, that would be really my first point.
But one other quick lesson to take away from this, it can be, for us or for science in general, it's often very helpful if models are all over the place, because they allow Linus to present a really nice post out there, where he shows that whatever models do in terms of Antarctic sea ice is related to many other things in the climate system, and so you can use Antarctic sea ice as a proxy for other properties that are harder to measure. And so I'm not too sad sometimes if models are all over, because it allows you to understand correlations in the climate system.
Maybe it's a bit too extreme for Antarctic sea ice. In the Arctic, that's okay, but in the Antarctic, probably it's a bit too much.
There's a recent paper by Will Hobbs who suggests there's a regime shift of Antarctic sea ice based on just observation statistical analysis. What are your opinions on how accurate that is?
I didn't read it in the details, so I cannot really comment. I think I've seen the presentation or the plots here and there, and I guess they argue on changes that occurred in the ocean system and Antarctic sea ice around 2016, but I don't know the detailed argument that is based in there. I wouldn't challenge. I would be confident in what they have analyzed makes sense. In general, that's my experience with this group of authors. There are plenty of reasons why we would think that mixed layer depth would be an issue for Antarctic sea ice, because it relates so much to the freeze update. That would be my first argument. like the ice advance is really related to mixed layer heat content. That would be a first thing. That seems to be obvious because sea ice needs to be at the freezing, seawater needs to be at the freezing points. That would be a first thing. And we also know that there are really strong heat exchange in winter between the subsurface ocean and the sea ice growth, and these are definitely probably not well represented. So there are lots of physical reasons to think that the sea ice seasonal cycle in the Southern Ocean is tightly linked with the surface ocean. Yeah, I think it's time to move on.